All right, let's take a look at problem 2. So in problem 2, we're asked to determine the temperature and phase of water from the following information. If the phase is a vapor-liquid mixture, report the fraction of vapor and liquid. So A, specific volume of water is 100 centimeters cubed per gram and pressure is 40 bars. Then B, specific volume of water is 100 centimeters cubed per gram and the pressure is 6 bars. Okay, well, let's do it. Okay, so the first thing I'm going to do is, since we're given specific volume and pressure, so specific volume is just like molar volume, but it uses mass instead of volume. The first thing I'm going to do is I'm going to draw my sketch of my phase diagram. So now remember, in the last problem, we drew a PT phase diagram. So in a PT phase diagram, my saturation curve is just a line, right? And the idea being is that when I have two phases at coexistence, those two phases are going to have the same temperature, pressure, and chemical potential, molar Gibbs free energy, or fugacity coefficient, depending on how you want to call it. But when I think about other properties, so things like molar volume or specific volume of those two phases are not going to be the same. Okay, the specific volume of the vapor phase is going to be greater than that of the liquid. I know that because I know the molecules are going to be further apart, right? And I know that they're not going to be equal. So when I draw P versus V phase diagram, instead of a line, saturation line like I had in a PT, I'm going to have an envelope. Okay, and so if I just draw a little sketch, let's see. So if I try and sketch a P versus V phase diagram, it's going to look something like this. Okay, and I'm just going to draw a dome. All right, the dome has a little shoulder at high volumes, because in the limit that V goes infinity or P goes to 0, I'm going to approach that ideal gas limit. Okay, all right, so we just said that when I'm at vapor-liquid coexistence, okay, the pressure, temperature, and chemical potential of those two phases are going to be the same. So if I draw an isobar across my phase envelope, okay, where it crosses my phase envelope, I'm going to have two phases in coexistence. Okay, the one with the greater specific volume or molar volume will correspond to my vapor phase, so that'd give me V vapor. The one with a smaller specific volume would give me my liquid phase. Okay, cool. So to the right of my envelope, I'll have vapor. Okay, to the left I'll have liquid. Okay, great. Now also on that phase diagram, we would have a series of isotherms. Okay, so an isotherm, all right, it's going to start up here, decrease until I hit my saturation curve, cross my phase envelope, because at equilibrium I have equality of temperatures and pressures, and then it'll again decrease down here in the vapor region. Okay, so the slope here, right, since this is P versus V, is going to be larger. It's going to be closer to infinity. If I were to flip it and do V versus P, it's going to be closer to 0, because my liquid phase is going to be much less compressible than my vapor phase. Okay, cool. Okay, and I could draw a series of overlapping isotherms. Sorry, stylus. And so if I were to draw a series of isotherms on here, right, again, I'm not going to judge your artistic abilities. Okay, you can see mine. Okay, but it would look something like this. Okay, and then ultimately at the critical point, all right, I get this inflection. All right, so the key being is that this is going to be my critical isotherm, Tc, and so as I move from right to left here, my temperature is decreasing. Okay, so T is decreasing. Okay, so as my temperature is decreasing as I move here, okay, how we get these names is if at this point I'm on my saturation curve, I have a saturated liquid. Okay, if I keep pressure constant, but I decrease the temperature, okay, that would correspond to, okay, so if I keep pressure constant, but I decrease the temperature, okay, so I'm walking along an isobar, bar, that's going to correspond to jumping over to the next isotherm, which is at, say, a lower temperature. All right, that's going to put me in the liquid phase. All right, that's where this is often called a subcooled liquid, and a PV besides, compressed. Right, it just depends on how you call it. The same token, if I'm over here, okay, so decreasing as I look over here, okay, temperature is increasing as I go from bottom up on this side. So if I'm a saturated vapor here, and I were to keep pressure constant but increase the temperature, that would correspond to jumping over to this isotherm. That would put me in the vapor phase. Okay, cool. Okay, so I'm going to erase some of these isotherms just because they make my plot even messier than it is. And then with that, we will have at this problem. Okay, cool. Okay, so let's start with A. So in A, we're told that the specific volume is 100 centimeters cubed per gram, and that the pressure is 40 bars. Okay, and we are asked to determine the phase of water, determine the temperature and phase of water from the following information. Okay, and so now kind of a thought exercise before we even look at the steam tables. So the Gibbs phase rule tells me that if I have a single component system at two-phase coexistence, I have just a single degree of freedom. Okay, cool. All right, so if we go to our steam tables, how do I want to say this? So if we are, a single component system at two-phase coexistence, so if I'm at two-phase coexistence, 40 bars is enough information to pin down the state of my system. If I'm a single phase, then I need 2 degrees of freedom, BP and V in this case. Okay, but we'll walk through this and see what this means. Okay, what this all entails. But anyways, so my strategy is going to be for a given pressure, so at 40 bars, I'm going to go to the steam tables and I'm going to look up VV and VL. Okay, so I'm going to look up VV and VL at a given T. Right, so that T would correspond to the temperature of this isotherm. Okay, and so then what I want to see is where my volume falls in relation to that. So if it happens then that if at that P, I read off this VL and that VV, if my specific volume in my system is in between VL and VV, that puts me in the two-phase region. That tells me I'm going to get phase splitting. So I'll have a two-phase system at coexistence, and I'll have, my vapor will have this molar volume, while my liquid will have that molar volume. Okay, so if I go through the same exercise, so at P I look at VL and VV, and so now if my specific volume is greater than the specific volume of the vapor or less than the specific volume of the liquid, well, that tells me then I'm either in the liquid region or the vapor region. Okay, so then how do I find temperature? So hopefully I'm in the superheated region, where with that molar volume and that pressure, I can go in and read off the temperature, but we're going to have to cross that bridge when we come to it. Okay, so again, the strategy is going to be for this pressure, I'm going to find VL and VV, and then if my specific volume falls in between the two of those, that tells me I'm in the two-phase region, so I must have two phases at coexistence, and so this would be the specific volume of that liquid. This would be the specific volume of that vapor in coexistence, and that saturation temperature would be my temperature, right? T set at that P. Right? Remember, if I have a single component system at two-phase coexistence, I have just a single degree of freedom. Right? So P is enough to pin down the state of my system. Now, if I look up VL and VV, and I find that my V is greater than VV, then I'm over here in the superheated vapor region. So then I'll go to my superheated steam tables, and to find T, I'll need to find the temperature for that given volume and pressure combination. Okay, cool. That's it. All right, so let's look at A. So 40 bars. Okay, so I'm going to go to my steam tables. Okay, so these are the superheated steam tables which we looked at in the last problem. So let's go down to 40 bars. Okay, 40 bars. Okay, all right, now units. So let's take a pause. So if I go back to the top of the steam tables, which is flipped, pressure is bars, temperature is degrees C, U is kilojoules per kilogram. They don't give me V. Okay, so let's try and get a reference point. So at 32.88, liquid is 0.001. Let's go over here. So what I want to look at is at, say, at 25 degrees C. I know the density of water is, 1 gram per cc. So if I'm about 24, 25, VL here, so again at 1 atm and 25 degrees C, so essentially at 25 degrees C we assume it's incompressible. I know liquid densities could be 1 gram per cc, or specific volume then would be 1 cc per gram. Here it's a factor of 3 different, right? Okay, so it must be meters cubed per kilogram. All right, so let's do, if I come back here, and let's do a quick sanity check. So if I have 1 gram, so 1 centimeter cubed per gram, okay, I'm going to multiply by 1,000 grams. Okay, and let's do SI prefixes, make it easier on myself. So 10 to the 3 grams per kilogram, and then I'm going to have 100 cubed centimeters cubed, right? So per meter cubed, because there's 100 centimeters per meter. So this would be 10 raised to the power 10 to the 2 raised to the power of 3, so that'd be 10 to the 6, and I need to flip it over. So this would be 1 meter cubed per 10 to the 6 centimeters cubed, right? So this 10 to the 3 over 10 to the 6 would give me a factor of dividing by 1,000. Okay, so this would be 1 times 10 to the negative 3 meters cubed per kilogram. Okay, so my sanity check then. Yep, so VL is going to have units of meters cubed per kilogram. Okay, so the first thing I'm going to do then is let's convert this. So if I go to A, so if the conversion factor is 1,000, okay, 1, 2, 3, okay, this is going to be 0.1 meters cubed per kilogram, and my pressure is 40 bars. Okay, all right, sorry. The book was missing units of volume, so meters cubed per kilogram. So getting back on topic, I'm looking for a pressure of 40 bars. Okay, so 40 bars here. Okay, I have the VL is 0.00125. Okay, so VL is 0.00125. Okay, and I'll just ignore the units for now. VV is 0.0498. 0.498. All right, so now let's compare. So V is 0.1, okay? So I find that V is greater than VV, okay? So what that tells me then is I'm going to be over here in the superheated region, okay? So question now is, what temperature do I have, okay? So if I'm in the superheated region, all right, so I'm a single component, single phase system, so I have 2 degrees of freedom. Okay, so now that I know I'm a superheated vapor, okay, my system will be pinned down by this pressure and that volume. Okay, so I go back over to my steam tables. Okay, so 40 bars. Okay, now I'm going to go to the superheated region. And what I'm looking for is at what temperature do I have a specific volume of 0.1? Okay, and what I find is it's somewhere between 600 and 650, right? I'm going to need to interpolate. Okay, so I'm looking for at the pressure of 40 bars, what temperature gives me a specific volume of 0.1, and I see it's going to be between 600 and 650. And so for your homework, you're going to need to interpolate. Okay, so just make a note. T is between 600 and 650 C. All right, so that one you would need to interpolate. Okay, let's take a look at B. Oops, so we got space here. So come on. Oh, here we go. So B. Again, I'm apologizing. New tab, new webcam, new everything. Okay, so B. V again is going to be 0.1 meters cubed per kilogram, and pressure 6 bars. Okay, and V is going to be equal to 0.1 kilograms per, or meters cubed per kilogram. Come on. Okay, that's meters cubed per kilogram. Okay, and pressure is 6 bar. Okay, so I go over to my superheated steam tables. 6 bars. Okay, I have that. Okay, VL is 0.00110. 0.00110, and the specific volume of my vapor is 0.3156. 0.3156. Okay, so I find that V is between VL and VV. Okay, so it must have two-phase. So I have a two-phase mixture with saturation temperature. So a temperature of 6 bars, 158.83. 158.83 degrees C. Okay. Cool. So I'm two-phase. There's my temperature. Again, I know I'm two-phase because for that pressure, my specific volume is between the specific volume of my liquid and vapor phase, along that iso bar. So it puts me in the two-phase region. So I can find the temperature as the temperature at coexistence at that P. Okay, but I'm not done yet because it tells us that if we have a vapor-liquid mixture, report the fraction of vapor and liquid. Okay, so fraction would be how much is what fraction of the total amount of liquid is vapor and how much is liquid. Okay, so basically we need to write down two conservation equations. So now the idea we can have in our head is, again, you can think of it as your piston cylinder where the pressure is fixed, but I have this closed system at this pressure or that temperature, and then V is going to be the total the specific volume of my system. So I have this closed system in which I have a vapor in equilibrium with the liquid. Okay, so the V, the specific volume of that system, would be the total volume divided by the total mass. Okay. Now, the specific volume of my system is going to be different than the specific volume of what's on top, my vapor, and what's on the bottom, my liquid. Okay. But the two things I have going for me is if I compute the volume occupied by the vapor and volume occupied by the liquid, I know that the two of those need to sum to give me the volume of my system. And then the other thing I have working for me is that I know that if I know the mass of my vapor and the mass of my liquid, that has to sum to give me my total mass. And so with that, essentially we come up with two conservation equations. Okay, so one would be the volume case. So if I know the total mass of my system and the specific volume of my system. This gives me the total volume of my system. Okay, that has to be equal to the mass of my liquid times the specific volume of my liquid plus the mass of my vapor plus the specific volume of my vapor phase. Okay, and then we said conservation of mass, so M has to be equal to ml plus mv. Okay, so we know V. Okay, we know VL, right? I just looked those up. I looked that up. I know VV. Okay, and so basically what we're trying to solve for is ml relative to m and mv relative to m. So one way you could think of this is we adopt a basis. We assume, say, m is 1 kilogram. Okay, so if I assume a basis that m is 1 kilogram, right, and essentially a basis is needed to define the extent of my system, I can then solve for ml and mv. Right, I have a system of two equations with two unknowns, which you can solve for ml and mv. Right, and so in theory, ml and mv will have units of kilograms, since we just assumed a basis of a mass of 1 kilogram. But what you really want is ml relative to m and mv relative to m. Right, so you can convert that to a fraction. Okay. So you would need to go ahead and calculate ml and mv, but it's just a matter of solving those two equations with two unknowns. Okay, hope that helps.